Okay, so we're looking at Chapter 1, Section 3, and we're on day 1 of that. And we're talking about continuity and in behavior. Today we're talking about continuity. So part 1 is continuity. And basically you're asking yourself, is there a y value at the given x value? And that's basically kind of what you're thinking about. Is there a y value, a real one? Like it exists in real numbers. So first, we're going to define a continuous function. Continuous functions have no breaks, gaps, or holes. So the graph continues on from start to finish with no breaks, gaps, holes, anything like that. So if you were to trace the function, trace the graph of the function, you would put your pencil down and you would not have to pick it up at all, and you could graph the whole thing without picking your pencil up because there's no breaks. It's continuous all the way through. So the example is determine whether f of x equals 2x squared minus 3x plus 1 is continuous at x equals 2. All right, so we're given an x value and we're asked, is the graph continuous at that x value? Or is there a y value for that x value? So to figure that out, what we're going to do is plug in for when x is 2. So plug in or evaluate the function at 2. So we take the function, and the way I've been telling you to when you use a formula is to write a blank everywhere there's an x if you're going to fill in something for x. So f of blank equals 2 blank squared minus 3 times blank plus 1. So I took my function and I left blanks everywhere there was an x. And now I'm going to take x is 2 and I'm going to evaluate f of 2. So I plug in a 2 everywhere there was an x. So here I'm evaluating. I have 2 squared, that's 4 times 2. That gives me an 8. Negative 3 times 2 is negative 6 plus 1. So I have 8 minus 6 is 2 plus 1. That gives me 3. Okay, so if I'm asking, is there a y value at that given x value? Well, I see it is 3. So now I can answer my question. I can say, formally, the limit, LIM, and that's written small, and underneath it, x with an arrow, as x approaches 2, the function f of x equals 3. The limit as x approaches 2 of f of x is 3. Therefore, f of x is continuous. We're talking about it's continuous at x is 2. So this, when in my limit notation, this 2 came from the problem where I was told I'm evaluating. I was told I'm evaluating at x equals 2. So I'm writing the limit at 2 because that's where it told me to look. And I know that I have that it's continuous because I'm looking also at the value that I got when I evaluated at 2. The number 3, that's a real number. Since it's a real number, I can graph it. It exists in the domain of real numbers. If it was an imaginary value, then it would not exist, right? I can't graph an imaginary number on the xy coordinate plane because those are imaginary. But if it's real, then I can graph it. All right, so that's the first part, continuity. So is it when it is continuous? Then we have discontinuity. So now we're going to talk about discontinuity. And we have 3 types. Three types of discontinuity. The first type is an infinite discontinuity. An infinite discontinuity. We know to look for an infinite discontinuity if we have a rational function. So with rational functions, because rational functions have vertical asymptotes. Vertical asymptotes, which I'm going to call VA. Vertical asymptotes. So an example, if we're given the function f of x equals x plus 1 over x minus 2, whenever you're given a rational function, the first thing you want to do is see, can I simplify this? Well, can I factor it? It's already in its factors. So x plus 1 on top, x minus 2 on bottom, that's it. But you also should remember that the same as rational functions as with all fractions is you cannot have a denominator equal to 0 in order for it to exist, right? You cannot divide by 0. So we have to take this denominator, x minus 2, and set it equal to 0. So x equals 2. That gives us a vertical asymptote at x equals 2. So if we did a quick sketch of this rational function, it'd be like, then this is not actual, just a quick representation of what it might look like. There is a vertical asymptote, or an infinite discontinuity, at x equals 2. We can write that in limit notation. The limit as x approaches 2 of the function f of x equals, so what's the y value at 2? Well, there isn't one because there's that asymptote there, so it does not exist. DNE does not exist. Therefore, infinite discontinuity. And we got the 2 in our limit notation is coming from what made the denominator equal to 0. If it was the first problem, oops, there it is. The first problem gave us an x to evaluate at. The second one did not. But we knew what it was because the denominator would be 0 at 2. Okay, so then the second type will be a removable discontinuity. A removable discontinuity, you have a removable when you have a rational, if you have rational functions, with common factors canceled out. Is when you cancel the factors, when you simplify your rational function, when you cancel your factors, you create a hole in your graph. So, holes. Let's do an example here. When f of x equals, the numerator is x squared minus 9, and the denominator is x minus 3. So if you're given this problem, if you have a rational, you should see, can I factor this any further? Yes, I can. Hopefully when you see that numerator, x squared minus 9, you think difference of squares, because you have a perfect square, subtraction, and another perfect square. So I can factor x squared minus 9 into x plus 3, x minus 3. And then x minus 3 is what's in the bottom. So if I factor the top, now I have a common factor in the top and the bottom. So I can remove them, right? You cancel them out, you're removing them from the equation. And all that's left is x plus 3. So right here, since I remove x minus 3, I create a hole at x equals 3. Because I removed it. So earlier I was asked, well, how do you know it's x equals 3? Well, if I remove x, the factor x minus 3, if I set it equal to 0 and solve it, then add the 3 to both sides and I get x equals 3. So I can write this as the limit as x approaches 3, f of x equals, so is there a y value at 3? Well, no, there's not. It does not exist because I just removed it from the function. So if I were to graph that, since we canceled the factors, our function is just x plus 3 now, which would be this line, graph of a line. However, at 1, 2, 3, when x is 3, we would have to go up here and put a hole in the graph at x is 3. So if we looked at the graph, is there a y value at 3? No, we removed it. There's a hole there, so it does not exist. Therefore, removable discontinuity. And we knew in limit notation we were using a 3 here because that is what we got when we set the denominator equal to 0. Okay. We have one more type, because I said we had 3 types of discontinuities. The third type is a jump discontinuity. So type 3 is a jump. You might have a jump discontinuity whenever you're dealing with a piecewise function. So piecewise, piecewise. And that usually functions. Usually. There's also a step function, but in general we can say piecewise. All right. So the example here, if you were given f of x equals set 1 over x, comma, for x's less than 0, and x for x's greater than or equal to 0. That's a piecewise function. It's broken up by the domain restrictions. When x is less than 0, all the negative values, we follow 1 over x. When x is 0 or greater, we follow the function f of x equals x. So it's broken into pieces based on its domain. All right, so to evaluate this one, we're going to plug in. And we're going to use these, whatever value is here. So wherever your domain is split up. Use the number from the domain restrictions. Use the number from domain restrictions. So if we're going to do, so 0 is the domain restriction number, we're going to do f of 0. So f of, and we're going to do zeros. And you have to do both of them. So we have 1 over 0. And then the other one is just 0. So 1 over 0, when we evaluate 1 over 0, that's 1 divided by 0. Nothing. It does. You can't, right? You cannot divide by 0. If you do 1 divided by 0 in your calculator, you get an error. So it's not an element of real numbers. So we're going to do this. This is capital E. Put a line through it. It's not an element of a set of real numbers. But f of 0, there's nothing to calculate for the other one. It's just 0, right? So because these don't give us the same, these are not the same. That tells us we have a jump. So we evaluate a certain x value and we get 2 things that are not the same. Leads us to a jump. And you can see that on the graph. So here if we graph this, On the left side, so the negative values, that's whenever we're graphing x is less than 0, it's 1 over x. So we know we have that, an asymptote, and it looks like this, sort of. Just a quick sketch of what it looks like. And then on the right-hand side, so x is greater than or equal to 0, that starts at 0. And at 0, it's a or equal to, so it's a solid dot, and it's the linear function x. So at 0, it's just the graph of x. That's a piecewise because it's in 2 pieces. So here, this one's going towards this vertical asymptote, and it goes down. It almost gets to 0, but never quite reaches it. And then at 0, it jumps up and is taken care of in the second part. So it's all of the x values are covered. It's just not. It's just by 2 different pieces of the graph. So the limit as x approaches 0 of f of x, it does not exist, D and E. Therefore, there is a jump discontinuity. So again, this number that where x goes to, it comes from this domain restriction. So this is also telling you that right there. All right, so your assignment is on page 30. And I'm going to have you do numbers 1 through 10 plus number 59.